I need to tell you something that most scientists are reluctant to say in public. Not because it is wrong, not because it is fringe, not because it belongs in the category of speculation that responsible scientists are supposed to keep at arm's length from serious discourse, but because it is the kind of statement that once you really hear it, once you really let it land, changes something in the way you experience reality. And most scientists are trained to communicate carefully, to hedge, to qualify, to present conclusions with the appropriate uncertainty intervals and the appropriate caveats and the appropriate professional distance that keeps the emotional weight of the idea at arm's length. I am going to dispense with that distance today. Here is the statement, the thing that most cosmologists now believe, but that almost nobody says plainly. We do not know what came before the Big Bang. We do not know if anything came before the Big Bang. We do not know if the concept of before even applies to the Big Bang. Behavior and the data we have collected about the structure and geometry and large-scale behavior of our universe contains anomalies, real anomalies, measured anomalies, anomalies that our best models cannot fully explain. And some of those anomalies are consistent with the possibility that something existed before our universe began, that something left marks on the fabric of our cosmos, the way a great storm leaves marks on a landscape long after the storm has passed. Something was here before us. And the reason scientists are unsettled by this is not because it is crazy, is because it might not be crazy. Because the mathematics that describes it is coherent, because the data that hints at it is real, because the implications of it, if true, are so profound and so disorienting that they require a fundamental revision of what we mean by the word existence, ban. So let us go there all the way without flinching bass. Let us start with the question that every child asks and that every physicist has had to eventually confront with uncomfortable honesty. What came before the Big Bang? The standard answer, the careful answer, the answer that physicists have been giving for decades is this: the question does not make sense. Time itself began at the Big Bang, before the Big Bang. There was no before, because before is a temporal relationship, and time did not exist before the Big Bang. Asking what came before the Big Bang is like asking what is south of the South Pole. The question assumes a framework that does not apply. That is a clean answer. It is philosophically satisfying in a certain way. It closes the question before it can cause too much trouble. And for decades, it was the answer. The official answer. The answer that got you through your cosmology exam. Problem. But here is the problem. That answer is only as good as the assumption that time truly began at the Big Bang. And that assumption is only as good as our theory of what happened at the Big Bang and our theory of what happened at the Big Bang. General relativity applied to the early universe breaks down at the moment of the Big Bang itself, produces a singularity, infinite density, infinite temperature, infinite curvature of space-time. And as I have told you before, when your equations produce infinity, it is not telling you that something infinite exists. It is telling you that your theory has failed, that you have pushed it beyond its domain of validity. General relativity cannot tell us what happened at t equals 0, the moment of the Big Bang, because general relativity breaks down at t equals 0 fast, which means it also cannot tell us with certainty that time began at t equals 0. That is a claim about what happened at or before the regime where the theory fails. It is an extrapolation beyond the edge of the theory's validity. And extrapolations beyond the edge of a theory's validity are precisely the places where surprising things tend to happen. When physicists apply quantum mechanical thinking to the Big Bang, when they try to describe the very early universe using a theory that takes seriously the quantum nature of space-time itself, something changes. The singularity goes away. In many approaches to quantum cosmology, the infinite density singularity that general relativity predicts is softened by quantum effects. The density reaches a maximum, an extraordinarily high density, the Planck density, about 10 to the power of 96 kilograms per cubic meter. Quantum. And then instead of continuing to increase toward infinity, the quantum repulsive effects kick in and the collapse reverses. Or the expansion emerges from a quantum tunneling event. Or the geometry transitions smoothly through what classical theory describes as a singular point, cost. And when the singularity goes away, so does the definitive beginning of time. So does the certainty that there was no before. In several serious theoretical frameworks being actively pursued by serious physicists, time did not begin at the Big Bang. The Big Bang was an event in time, a dramatic event, a cosmically significant event, the moment from which our particular universe began its expansion, but not the beginning of time itself. And if time did not begin at the Big Bang, then the question of what came before is not meaningless. It is the most important question in cosmology. Let me tell you about some of the answers that physicists have proposed. And I want to be clear that these are not science fiction. These are not the speculations of fringe theorists working outside the mainstream. These are ideas developed by some of the most accomplished theoretical physicists alive, published in peer-reviewed journals, presented at major conferences, taken seriously by the scientific community, even when they are deeply uncomfortable. The first is the cyclic universe. The idea that the Big Bang was not a beginning, but a transition. One moment in an eternal sequence of cosmic expansions and contractions, or cosmic collisions, depending on which version of the theory you are looking at. The oldest version of this idea goes back decades. The oscillating universe. The idea that the universe expands after each Big Bang, and then eventually the expansion slows and reverses under the influence of gravity, and the universe contracts back down to a big crunch, a maximum compression, and then bounces. Another Big Bang, another expansion, cycle after cycle, eternal in both directions. No beginning, no end. Just an infinite sequence of cosmic births and deaths. This version ran into problems. The discovery that the universe's expansion is accelerating rather than decelerating made a future big crunch unlikely given current understanding of dark energy. And thermodynamics posed a challenge. Each cycle of expansion and contraction should increase the entropy of the universe, the disorder. And if cycles have been going on forever, the entropy should have reached its maximum long ago. The universe should be in a state of maximum disorder, which it manifestly is not. We have structure, we have stars and galaxies and complex chemistry. We have astonishingly low entropy for a universe that is supposed to have been cycling forever. But the cyclic idea did not die, it evolved. And the modern version is considerably more sophisticated and considerably more disturbing. In the 1990s and 2000s, physicists Paul Steinhardt and Neil Turok developed what they called the ekpyrotic universe, drawing on string theory and specifically on the idea of extra dimensions. In string theory, the universe we perceive as three-dimensional space plus time is actually a higher dimensional structure. Our universe might be a three-dimensional membrane, a brain, floating in a higher dimensional space alongside other brains, other universes, other three-dimensional worlds separated from ours. Not in the spatial dimensions we can perceive, but in an extra dimension we cannot directly access. In the ekpyrotic model, our Big Bang was not a singularity. It was a collision, two brains, our universe brain and another brain, moving toward each other through the extra dimension, colliding. The collision released an enormous amount of energy. That energy manifested in our brain as the hot, dense plasma of the early universe. The Big Bang and the expansion of our universe after the collision is the aftermath of that impact. The two brains bouncing apart after their collision and then slowly being drawn back together by gravitational attraction through the extra dimension until they collide again. Another Big Bang, another cycle. Now here is what makes this genuinely unsettling rather than merely theoretically interesting. The ekpyrotic model makes predictions about the pattern of fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang, the most detailed map we have of the early universe. And those predictions are different from the predictions of standard inflationary cosmology. In standard inflation, the primordial gravitational waves, the ripples in the fabric of space-time generated by the rapid expansion of the early universe, should leave a specific imprint on the cosmic microwave background, a specific pattern of polarization called B modes. In the ekpyrotic model, the primordial gravitational wave signal should be essentially undetectable, much weaker than inflation predicts. We have been searching for primordial B-mode polarization in the cosmic microwave background for years. Multiple experiments, BICEP, Keck array, the South Pole telescope, the Planck satellite, and we have not definitively detected a primordial B-mode signal. We have set increasingly tight upper limits on how strong it can be, and those upper limits are squeezing the inflationary models, making the simplest versions of inflation increasingly difficult to accommodate. The absence of a signal predicted by inflation and consistent with the ekpyrotic model is not proof that the ekpyrotic model is right. Absence of evidence is not evidence of absence at the level of sensitivity we have currently achieved, but it is a data point, a real data point. And it keeps the cyclic idea alive as a serious contender. But the cyclic universe is not the only pre-Big Bang scenario that the physics supports. And it is not the one that I think is most deeply unsettling. Let me tell you about conformal cyclic cosmology, because this is the idea that I find genuinely haunting, not in a supernatural sense, in a deep physical sense, in the sense that it implies something so strange about the relationship between past and future and between one universe and the next, that it reframes the entire question of what was here before us. Conformal cyclic cosmology was developed by the mathematician and physicist Roger Penrose, one of the greatest mathematical minds of the 20th and 21st century. The person who proved the singularity theorems alongside Stephen Hawking, who developed the mathematics of twistors, who has contributed more to our mathematical understanding of space-time than almost anyone alive. And Penrose's idea is this: the universe begins with the Big Bang, hot, dense, smooth, and it expands, and over billions of years it evolves. Stars form and die. Galaxies organize themselves. Black holes form the largest structures in the universe, assemble under gravity, and eventually, in the far, far future, a future so distant, it makes the current age of the universe look like a nanosecond. The universe approaches what physicists call the heat death, the state of maximum entropy, the state where no more useful work can be done, where everything that can happen has happened, where the universe is cold and dark and expanding forever. In the distant future of such a universe, essentially all the matter has either fallen into black holes or dispersed into radiation. The black holes themselves eventually evaporate through Hawking radiation, radiating away their mass as a diffuse bath of very low energy photons. And what you are left with is a universe filled with photons, just photons. An expanding universe of cold diffuse radiation with nothing else in it. Because. Now, here is the key physical insight that Penrose had. Photons are massless, and massless particles have a remarkable property. They do not experience time in the way that massive objects do. For a photon traversing the universe, the concept of elapsed time is not well defined. A photon emitted from the Big Bang plasma and a photon emitted by the last evaporating black hole in the far future are, in a certain mathematical sense, equivalent. They are both massless particles propagating through space-time. And in the mathematical framework called conformal geometry, which preserves angles and shapes but not scales, the very large-scale structure of the future universe and the very small-scale structure of the early universe have a mathematical equivalence. Penrose argues that the remote future of one cosmic cycle, a cold, dark universe filled with nothing but photons, is mathematically identical to the Big Bang of the next cycle. The end of one universe and the beginning of the next are the same geometric structure described in different mathematical coordinates. The universe does not need a mechanism to bounce or to collide or to tunnel. It simply continues. The end is the beginning. The death of one universe is the birth of the next, seamlessly, without any special event, without any singularity, without any intervention. The universe is a Ouroboros, the ancient symbol of the serpent eating its own tail. The end consuming the beginning to produce the beginning again. Con. And here is what makes conformal cyclic cosmology genuinely testable and genuinely unsettling at the same time. If the current universe is not the first cycle, then the previous cycle left marks. The previous universe's black holes, as they merged and collided, produced gravitational waves. Enormous gravitational waves. The largest gravitational waves ever produced. And those gravitational waves from the previous cosmic cycle should have left an imprint, a subtle pattern in the cosmic microwave background of our universe. Penrose calls them Hawking points, circular regions in the cosmic microwave background where the temperature fluctuations are slightly different from their surroundings, caused by the gravitational waves from the last evaporating supermassive black holes of the previous universe, focusing energy into specific regions of the early plasma of our universe. Are they there? Penrose and his colleagues claim to have found evidence for them. Circular patterns in the cosmic microwave background data consistent with what Hawking points should look like. Other scientists have disputed the statistical significance. The debate continues. It is not settled. But here is the thing. We have the data. We have the maps of the cosmic microwave background with enough resolution and sensitivity to potentially see these signals if they are there. The question of whether the previous universe left fingerprints on our universe is not a purely philosophical question. It is an empirical question. It's one that the data might be able to answer. The idea that we might find evidence in the cosmic microwave background. The oldest light in our universe of events that happened in a previous universe before our Big Bang. That is not science fiction. That is observational cosmology at the frontier. But I want to go somewhere even stranger, because the pre-Big Bang scenarios I have described so far are all, in some sense, comfortable. They imagine a previous universe that was like ours, different perhaps in its details, but governed by the same physics, playing by the same rules, containing the same kinds of structures, matter and energy and black holes and radiation, familiar things in unfamiliar arrangements. What if what came before was not like our universe at all? What if what was here before us played by completely different rules? This is where the landscape of string theory enters the picture. And this is where I think the genuinely horrifying possibilities live. Not horrifying in the sense of monsters and darkness, horrifying in the sense of scale, in the sense of what it means for us if it is true. String theory predicts the existence of an enormous number of possible universes, each one governed by a different set of physical laws, different values of the fundamental constants, different numbers of spatial dimensions, different particle content, different forces. The number of possible universes in the string theory landscape is estimated at something like 10 to the power of 500. A number so large, it is not just astronomically large, it is incomprehensibly large. The number of atoms in the observable universe is about 10 to the power of 80. The number of possible universes in the string theory landscape is 10 to the power of 500. The landscape makes our observable universe look like a single grain of sand on every beach on Earth compared to the total number of grains. Commerce. And in the framework of eternal inflation, all of these possible universes are being realized somewhere in some bubble of the eternally inflating metaverse. Every possible set of physical laws exists in some region of the larger reality, our universe, with our specific values of the fundamental constants, our specific particle masses and force strengths and cosmological constant is one bubble, one realization, one possibility among 10 to the power of 500 others. What was here before us in this framework? Other universes, universes with different physics, universes where the forces did not balance the way they do in ours, where atoms could not form, where stars could not ignite, where carbon could not be synthesized, where chemistry could not emerge, where life was not possible. Universes that expanded and then collapsed back in a fraction of a second because the cosmological constant was the wrong sign. Universes that expanded so rapidly that matter never had time to clump together and form structures. Universes where the strong nuclear force was slightly weaker and protons could not bind together to form nuclei, and there was nothing but hydrogen forever. Most of the universes that came before ours in this picture were sterile, empty of complexity, empty of chemistry, empty of life, empty of anything we would recognize as interesting. And ours happened to have the right combination of constants to allow the extraordinary cascade of complexity that produced galaxies and stars and planets and oceans and organisms. And the question of why our universe has the specific physical constants it does, why gravity is as strong as it is and not stronger or weaker, why the cosmological constant is as small as it is, why the mass of the electron is what it is. These are questions that have no answer within our universe. The constants are what they are. We measure them, we plug them into our equations, and our equations describe reality with extraordinary precision. But we cannot derive them from first principles. We cannot explain why they have the values they do. In the landscape picture, the answer is selection. We live in a universe with life-permitting constants because those are the only universes in which anyone is around to ask the question. The vast majority of universes have constants that do not permit life, and those universes exist. In the landscape picture, they are as real as ours. But they are not asking questions about themselves. We are asking because we can, because our universe happened to have the right constants, not by design, not by intention, but by the sheer combinatorial exhaustiveness of a process that realizes every possibility. And what came before us in this picture is the process itself. The eternally inflating metaverse that has been spawning bubble universes for longer than any clock could measure, longer than any number we have convenient names for, perhaps forever in both directions. A churning quantum foam of inflating space that is the ultimate context in which our universe is embedded prior to our Big Bang, coexisting with our universe right now beyond our observable horizon, continuing after everything in our universe has evaporated. Something was here before us. The process that made us the quantum gravitational churning of eternal inflation. The landscape of possibilities working itself out in cosmic time that was here before us, and it is still here right now, beyond the boundary of what we can see in the space that our observable universe is embedded in, still inflating, still spawning bubble universes, still realizing possibilities with no knowledge of us and no concern for us and no endpoint visible from within any of those bubbles. That is what was here before us. In the broadest sense, in the sense that the most ambitious theories of modern physics are pointing toward. It's core. And now I want to tell you about the anomalies, the actual data, the things in our universe that should not be there if our universe had a clean, uneventful beginning with nothing before it. Because the theory is one thing. What makes this genuinely unsettling is the data, the cosmic microwave background, the oldest light in the universe, the map of the infant cosmos at 3,800,000 years old is the most precisely measured thing in all of cosmology. The Planck satellite mapped it with such extraordinary precision that the map contains more information than we know how to fully analyze. And in that map, there are things that should not be there. I told you about some of these anomalies when we talked about the edge of the universe. The suppression of large-scale power, the hemispherical asymmetry, the cold spot. These are real features in the real data that have survived every systematic check, every reanalysis, every attempt to explain them away as measurement artifacts. But there are others. And some of them are specifically consistent with signals from before the Big Bang. The Planck satellite detected a pattern of correlations in the cosmic microwave background that extends across the largest scales of the observable universe, the full sky. Correlations between temperature fluctuations on opposite sides of the sky that are slightly different from what the standard inflationary model predicts. And here's the thing. One of the proposed explanations for these anomalous large-scale correlations is that they are remnants of pre-inflationary physics of whatever existed before the inflationary period that set up the initial conditions of our universe. In standard inflation, the inflationary expansion is so rapid and so extensive that it erases essentially all information about what came before it. It smooths away the fluctuations. It homogenizes the universe. It is like a cosmic reset button. Whatever existed before inflation, its physical imprints should be washed away by the expansion. The universe we observe should be a clean slate, a pristine product of inflation with no memory of anything that came before. Process. But the large-scale anomalies might be telling us that inflation was not quite long enough, that it did not fully erase the pre-inflationary state, that some faint residual signal from before the inflationary epoch survived, imprinted on the largest scales of the cosmic microwave background. The largest scales, because those are the scales that carry the oldest information. The scales that were already established before inflation and that inflation only partially processed. If that interpretation is correct, and it is genuinely debated, we are looking at evidence of what existed before our universe in the oldest light in the cosmos. We are reading the faint handwriting of whatever came before in the pattern of temperature fluctuations across the sky. And then there is the axis of evil. I want to tell you about the axis of evil. And I want you to understand that this is not a nickname I invented for dramatic effect. This is the actual term used in the peer-reviewed scientific literature by actual cosmologists. It's named by the physicists Kate Land and João Magejo when they identified it in 2005. The axis of evil is an alignment, a completely unexpected and deeply puzzling alignment of features in the cosmic microwave background. The largest scale fluctuations in the cosmic microwave background, the quadrupole and the octopole. The biggest patterns across the entire sky are aligned with each other, and they're aligned with the plane of our solar system, and they're aligned with the direction of the equinoxes. In a universe that is supposed to be the same in every direction, in a universe where there is no preferred direction, in a universe where the large-scale structure should have no relationship whatsoever to the local structure of our solar system, this alignment exists. It should not be there. The probability of this alignment occurring by chance in a truly isotropic random universe is less than 1%. The statisticians have checked it repeatedly. The alignment is real. It is not a measurement artifact. It survived the transition from the WMAP satellite data to the Planck satellite data with even higher precision. It is there in the real universe. Mocking our models, nobody knows why. And the proposed explanations range from the mundane to the exotic systematic errors in the data, contamination from our own galaxy, statistical flukes that are less unlikely than they appear because of the way we choose which statistics to look at. These are the conservative explanations, and they have been extensively investigated, and none of them fully satisfactorily explain the alignment. The exotic explanations include topology, the universe wrapping around on itself in a specific direction, creating a preferred axis. They include the influence of a neighboring bubble universe in the eternal inflation landscape. A bubble collision that happened early in our universe's history and that imprinted a directional signal on the largest scales. They include pre-inflationary physics, a pre-existing structure in whatever existed before our Big Bang that survived the inflationary epoch and left this alignment as its signature. Something aligned the largest structures in the observable universe along a specific direction. And we do not know what. That is not a comfortable statement. And I'm not going to make it comfortable by offering a reassuring conventional explanation. The honest statement is, we do not know. And the fact that we do not know, after decades of the most precise measurements in the history of cosmology, after billions of dollars of satellites and telescopes and computing infrastructure, after thousands of physicists and mathematicians and data scientists working on the problem, after all of that, we still do not know. And that is either a scandal or an invitation. And I choose to see it as an invitation to go deeper, to question the assumptions that our models are built on, to consider possibilities that make us uncomfortable precisely because they are the possibilities that our data is pointing toward. Something is written in the oldest light in the universe, something that our standard model of cosmology did not predict, something that resists all the conventional explanations we have tried to apply to it. And some of the unconventional explanations, the ones that involve what was here before us, are at least as mathematically coherent as the conventional ones. The universe is trying to tell us something about its own origins, about what preceded it, about what it is embedded in, about whether our Big Bang was truly a beginning or merely a transition. And we are just barely beginning to learn how to listen. In part 2, we are going to go somewhere even stranger. We are going to talk about the specific physical structures that some physicists believe should not exist in a universe with a clean Big Bang beginning, but that appear to exist anyway. We are going to talk about what the second law of thermodynamics implies about the state of whatever preceded our universe. Bolts. We are going to talk about the Boltzmann brain paradox and why it is one of the most disturbing implications of modern cosmology. And we are going to confront the possibility that is perhaps the most unsettling of all. Not just that something was here before us, but that something might still be here. Now, coexisting with our universe in dimensions we cannot perceive, in regions we cannot observe, in a reality that contains ours the way an ocean contains a bubble, watching or not watching, which might be worse. I want to start with a thought experiment, not a gentle one, not the kind that eases you in with a familiar analogy before revealing something surprising. I want to start with the thought experiment that has kept more than one cosmologist awake at night. The one that, when you follow it all the way to its logical conclusion, produces a result so disturbing that some of the most brilliant physicists alive have described it as the most troubling idea in all of modern science. It is called the Boltzmann brain paradox, and it begins with a question that sounds almost trivial. Why is the universe so ordered? Think about what I am asking. The universe we observe is a place of extraordinary structure. Galaxies arranged in vast cosmic webs, stars organized into galaxies, planets orbiting stars, chemistry organized into molecules, molecules organized into cells, cells organized into organisms, organisms organized into ecosystems and civilizations and scientific communities that build satellites to map the oldest light in the universe. At every scale, from the subatomic to the cosmological, the universe exhibits structure, organization, low entropy, a state of affairs that is profoundly improbable from a purely statistical standpoint. The second law of thermodynamics tells us that closed systems evolve toward higher entropy, toward greater disorder, toward the most probable arrangement of their constituents. And the most probable arrangement of matter and energy in a universe of the size and age of ours is not galaxies and stars and planets and people. It is a diffuse uniform gas, a featureless soup, maximum entropy, maximum disorder. The heat death. We are nowhere near the heat death. We are in a universe of spectacular, improbable order. And the question is why? The standard answer involves the Big Bang. The universe began in an extraordinarily low entropy state, an extraordinarily ordered state. The hot, dense, smooth plasma of the early universe had low entropy, not because it was disordered, but because of the specific way its order was configured. Smooth in its distribution of matter, but with enormous gravitational potential energy waiting to be released, as that smoothness gave way to clumping and structure formation under gravity. And from that low entropy beginning, the universe has been evolving toward higher entropy ever since. Stars burning, black holes forming, structure emerging, and then eventually dispersing. We are in the middle of that journey between the extraordinary low entropy of the Big Bang and the maximum entropy of the far future heat death. This is the standard story. And it raises an immediate question that the standard story does not fully answer. Why did the universe begin in such a low entropy state? Because a low entropy beginning is extraordinarily improbable. If you imagine all the possible ways the universe could have begun, all the possible initial configurations of matter and energy, the vast, overwhelming majority of them are high entropy configurations, disordered, featureless, randomly distributed. The specific low entropy configuration that our Big Bang started from is fantastically unlikely by any naive probability measure. Ludwig Boltzmann, the 19th century Austrian physicist who developed statistical mechanics and gave us our modern understanding of entropy, wrestled with exactly this problem. Keen. And he proposed an answer that seemed reasonable at the time, but that has become increasingly disturbing as its implications have been worked out. Boltzmann proposed that in an eternal universe, in a state of maximum entropy, a universe that has reached the heat death and is sitting in a state of thermal equilibrium. Random fluctuations will occasionally and very rarely produce regions of lower entropy. Just by chance, the way that a room full of air molecules that are uniformly distributed might very occasionally have all the air molecules spontaneously move to one side of the room purely by random motion. It is extraordinarily unlikely, but in an infinite amount of time it will happen. Every possible fluctuation will happen given enough time. And in an eternal universe at maximum entropy, the fluctuations that occasionally occur include fluctuations into low entropy states, including states as low entropy as our observable universe. So perhaps our universe is one such fluctuation, a random statistical fluctuation from the eternal heat death of a much larger and much older universe that has been in thermal equilibrium for an incomprehensibly long time. Our Big Bang was not a true beginning. It was a statistical accident, a random burp of order in an eternal sea of disorder. Boltzmann thought this might explain why we find ourselves in a low entropy universe. We find ourselves here because this is where observers can exist. In the high entropy equilibrium regions, there are no observers. Only in the rare fluctuations to lower entropy do conditions arise that permit the existence of minds capable of asking questions. Now here is where the thought experiment becomes a nightmare. If the mechanism for producing our low entropy universe is random statistical fluctuation from a high entropy background, then we have to compare the probability of different kinds of fluctuations. And here is the crucial insight. Smaller fluctuations are vastly more probable than larger ones. The probability of a fluctuation decreases exponentially with its size. A fluctuation that produces a single atom from the thermal background is more probable than a fluctuation that produces 2 atoms. A fluctuation that produces a cubic centimeter of ordered matter is more probable than a fluctuation that produces a cubic meter of ordered matter, and so on, exponentially. With every order of magnitude increase in the size of the fluctuation, the probability drops by an incomprehensible amount. Now, consider what the smallest possible fluctuation that could produce an observer would look like. Not a whole universe with hundreds of billions of galaxies and billions of years of stellar evolution and a planet and an ecosystem and a civilization. Just the minimum necessary for a conscious, observing mind to exist for one moment. Asking itself why it finds itself in an ordered universe. That minimum fluctuation is a single brain, a single disembodied brain, spontaneously assembled from the thermal background, with all its neurons in the right configuration to have memories and experiences and thoughts, including the thought that it is in an ordered universe, calm, even though the universe around it is actually a high entropy thermal soup, and all those memories are false, implanted by the fluctuation itself. This is the Boltzmann brain. A fluctuation so much smaller and therefore so much more probable than a whole ordered universe, that if the Boltzmann mechanism is the explanation for why we exist in a low entropy state, then the overwhelming majority of observers in the universe should be Boltzmann brains, disembodied minds with false memories, momentarily fluctuated into existence from the thermal background, lasting for a fraction of a second before dissolving back into the soup. If Boltzmann brains are more probable than real observers in genuinely evolved universes, and the mathematics strongly suggests they are, Boltzmann, then the probability that you are a Boltzmann brain rather than a real observer in a real ordered universe is essentially 1. You are almost certainly a Boltzmann brain. Your memories are almost certainly false. The universe around you is almost certainly not what it appears to be. You flickered into existence moments ago from the thermal background with a complete set of false memories about a life you never lived and a universe you never inhabited. And you will dissolve back into disorder in a moment. I told you this one was not going to be comfortable. Now, of course, nobody actually believes they are a Boltzmann brain. And the reason nobody believes it is not purely psychological resistance to an unpleasant idea. It is that the Boltzmann brain conclusion is so absurd that it constitutes a reductio ad absurdum of the premise that led to it. If your theory predicts that the overwhelming majority of observers should be Boltzmann brains, and yet we are clearly not Boltzmann brains because our observations of the universe are consistent and coherent, and our memories accurately predict future observations in ways that false memories never could, then your theory is wrong. The Boltzmann mechanism cannot be the explanation for why we find ourselves in a low entropy universe. Something else has to explain it, cosmologist. And something else that most cosmologists fall back on is the Big Bang, a genuine thermodynamic beginning, a genuinely low entropy initial state that was not a fluctuation from a prior high entropy state, but rather a true beginning, or at least a beginning from a very different kind of prior state. One that was itself extraordinarily low entropy, not a high entropy thermal background, but something ordered, something structured, something with low entropy of its own praise. But now we have just pushed the problem back one step. If our Big Bang began in a low entropy state, and the Boltzmann mechanism cannot explain why, then what explains the low entropy of the Big Bang itself? What came before the Big Bang that set up such an extraordinarily ordered initial condition? Back. And we are back to the question that started this whole conversation. What was here before us? The Boltzmann brain paradox does not just haunt us as a logical curiosity. It actively constrains the theories we are allowed to propose about pre-Big Bang physics. Any theory that says the universe before our Big Bang was in a high entropy state runs directly into the Boltzmann brain problem. Any theory that says our Big Bang emerged as a fluctuation from a prior state of thermal equilibrium has to contend with the fact that such a mechanism predicts we should be Boltzmann brains, which we are not. So whatever was here before us was not a high entropy thermal bath. It was something with low entropy of its own, something ordered, something structured, something that had low entropy for reasons that themselves require explanation. The problem does not terminate. It recedes. Every answer generates a new question. Every explanation of the low entropy initial condition requires an explanation of why that initial condition had low entropy. It is turtles all the way down, unless we find a framework in which low entropy is somehow natural, generic, not requiring special explanation. A framework in which the arrow of time and the low entropy beginning of our universe emerge inevitably from the underlying physics rather than requiring a miraculous accident of initial conditions. That framework does not yet fully exist. Building it is one of the deepest unsolved problems in all of physics. And this connects to something I want to tell you about that I think is the most physically specific and the most observationally grounded piece of evidence that something strange is encoded in the structure of our universe. Something that points not just to a pre-Big Bang state, but to specific structures, specific objects, specific physical entities that should not exist in a universe with a clean, uneventful Big Bang beginning. They're called primordial black holes. And their story is one of the most interesting in contemporary cosmology. In the very early universe, in the first fraction of a second after the Big Bang density fluctuations in the hot plasma could have been large enough that some regions collapsed directly into black holes. Not from stellar collapse the way ordinary black holes form, rays, but from the direct gravitational collapse of overdense regions in the primordial plasma. These are called primordial black holes. And they would have a mass spectrum determined by the size of the density fluctuations that produce them. Some could be very massive, some could be very small. Much smaller than any black hole that could form from stellar collapse. Primordial black holes are a real prediction of the standard Big Bang model. They're expected to exist if the density fluctuations in the early universe were large enough in certain mass ranges. And there is observational evidence suggesting they might exist. Gravitational microlensing surveys have found hints of objects in the mass range consistent with primordial black holes in the halo of our galaxy. The gravitational wave detections by LIGO have found merging black holes with masses in ranges that are difficult to explain, purely from stellar evolution. Some of those merging black holes might be primordial. Praise. But here is where it gets interesting in the context of what was here before us. If the universe went through a pre-inflationary phase, if there was a period before inflation when the universe had a different physical character, when the density fluctuations had a different spectrum than the ones inflation generated. Primordial black holes produced in that pre-inflationary period would have a different mass spectrum, a different distribution. A fingerprint of the pre-inflationary state encoded in the population of primordial black holes that survived into the present universe. We are looking for that fingerprint. The LISA space-based gravitational wave detector, scheduled for launch in the 2030s, will be sensitive to the gravitational wave background produced by merging primordial black holes from the early universe. The statistical properties of that gravitational wave background carry information about the density fluctuation spectrum of the very early universe. Information that potentially reaches back to before the inflationary epoch, to before our Big Bang, in whatever sense before applies. We might be able to hear the echoes of what existed before us, not in the cosmic microwave background photons, not in the alignment of quadrupoles and octopoles, but in the gravitational wave background, in the space-time ripples produced by the merging of objects born in the first instance of our universe, or in the instance before our universe, in whatever phase preceded it. Gravity waves travel through space-time without being absorbed or scattered. They carry their information from the moment of their production to the moment of their detection without loss. They are the most transparent signal in the universe. And the gravitational wave background contains signals from the earliest moments of cosmic history, earlier than the cosmic microwave background, earlier than any electromagnetic signal can reach us, because the universe was opaque to light until 3,800,000 years after the Big Bang. Gravitational waves pass through that opacity as if it were not there, and they carry information from the moment of the Big Bang itself, and potentially from before. When LISA comes online, we will open a new window on the universe, a gravitational wave window that looks back further than any other telescope has ever seen, back to the first moments, and potentially back to the last moments of whatever came before, on there. Now, I want to tell you about something that is perhaps the most haunting possibility of all. Something that sits at the intersection of quantum mechanics and cosmology and information theory, and that I believe represents the deepest version of the question we have been asking all along: not just what was here before us, but whether what was here before us left something behind that is still here. Now, not as a fossil, not as an imprint in ancient light, but as an active, ongoing presence in the structure of reality. I want to talk about the vacuum. The quantum vacuum is not empty. This is one of the most important and least appreciated facts in all of physics. Empty space is not empty. At the quantum level, space is filled with a seething, churning froth of virtual particles. Particle-antiparticle pairs that pop into existence out of nothing and annihilate each other in times so short that the uncertainty principle permits their temporary existence. Without violating energy conservation, they are not real particles in the sense that they cannot be directly detected, but they have real physical effects. The Casimir effect, the Lamb shift in atomic energy levels, the anomalous magnetic moment of the electron, all measured, all confirmed, all consequences of the quantum vacuum fluctuations that fill what we naively call empty space. The energy of the quantum vacuum, the 0-point energy, the energy of these fluctuations, even when no real particles are present, is not zero. The vacuum has energy, and that energy gravitates. It contributes to the expansion of the universe. And in fact, the most natural interpretation of the cosmological constant, the dark energy that is causing the accelerating expansion of the universe, is that it is the energy density of the quantum vacuum. But here's the problem. When physicists calculate the energy density of the quantum vacuum using quantum field theory, they get a number, a specific number, and when they compare that number to the observed value of the cosmological constant, the two numbers differ by a factor of approximately 10 to the power of 120. 1 followed by 120 zeros. The theoretical prediction and the observed value differ by the largest discrepancy between a theoretical prediction and an observation in the history of science, by a factor that is so large it makes every other disagreement in physics look like a rounding error. This is called the cosmological constant problem. And it is not a minor technical issue. It is a catastrophic failure of our theoretical framework. Our best theory of quantum fields predicts a vacuum energy that is 10 to the 120 times larger than what we observe. If that predicted vacuum energy were real, the universe would have expanded so rapidly right after the Big Bang that no structure would ever have formed, no galaxies, no stars, no planets, no chemistry, no life, nothing but a rapidly dispersing dilute gas expanding toward infinite size in a tiny fraction of a second. Something is canceling the vacuum energy, reducing it from its theoretical value of 10 to the 120 to the observed value of essentially 1 inch, those units, with a precision of 120 decimal places. Whatever is doing that cancellation is doing it with extraordinary precision, and we do not know what it is. Now, here is the connection to what was here before us. One proposed resolution to the cosmological constant problem involves the idea that the vacuum energy is not a fixed fundamental constant, but rather a dynamical quantity, a field, something that can take different values in different regions of space, and that evolves over time, and that its current value, the value we observe, is not its natural fundamental value, but rather the value it relaxed to after some process of evolution. Some process that happened in the early universe, or before the early universe, or that is still ongoing at scales we cannot observe. If the vacuum energy is a dynamical field that relaxed to its current value, then the history of that relaxation is encoded in the current structure of the vacuum. The current state of empty space contains the memory of what it went through to get here. The vacuum around you right now, the nothing between the atoms in your hand and the walls of the room you are in, that nothing carries information. It carries the thermodynamic history of its own evolution process. It carries the signature of whatever process set the vacuum energy to the extraordinarily finely tuned value it has. Bang. And if that process happened before our Big Bang, if the vacuum we inhabit is a remnant of a pre-Big Bang state that went through some kind of phase transition or relaxation process to reach its current configuration, then the vacuum is the most direct evidence of what came before us. Not an imprint in ancient light, not an alignment of temperature fluctuations. The vacuum itself, the ground state of reality. The thing that fills all of space is a fossil of the pre-Big Bang state. We are swimming in the remnant of what was here before us. It surrounds us. It fills the space between every atom in our bodies. It is the medium through which every photon and every gravitational wave and every particle propagates. And it carries within its structure the memory of what it was before our universe began. Conjures. Now, I want to bring you to the question that I think is philosophically the most vertiginous, the one that I save for last, because it requires everything we have discussed to fully appreciate. We have been asking what was here before us, and we have found several serious, scientifically grounded answers. Cyclic universes, ekpyrotic brain collisions, conformal cyclic cosmology, that eternal inflation with a landscape of pre-existing universes, pre-inflationary quantum gravity states. All of these are answers to what came before, what existed prior to our Big Bang, what left its marks on our universe that we can still read today. But there is a different version of the question that I have been building toward all along, and it is this: is it still here? Not as a fossil, not as an imprint, not as an echo in ancient light or a pattern in the cosmic microwave background, but as an active, ongoing reality, coexisting with our universe right now. In the same way that two rooms in the same building coexist, even though the inhabitants of one cannot directly perceive the other, in the eternal inflation framework, the answer is unambiguously yes. The eternally inflating metaverse that spawned our bubble universe is still inflating right now. Right now, as you read this, beyond the boundary of our observable universe, beyond the edge of what we can ever see, other bubble universes are still being spawned. Other Big Bangs are still happening. Other regions of inflating space are still expanding exponentially, spawning new bubbles, creating new universes with new physics. The process that made us is still running. It never stopped. It will never stop. It is eternal. And it is happening right now in the reality that surrounds our observable universe. The way an ocean surrounds a bubble, we cannot see it. We cannot reach it. We cannot communicate with it. The boundary of our bubble universe is receding from us faster than light. Nothing from beyond that boundary can ever reach us. We are permanently sealed inside our bubble, surrounded by a reality we can infer but never observe. A reality that is incomparably larger than everything we can see. A reality that contains our universe the way a universe contains an atom. Hottivus, and in the string theory landscape, the reality beyond our bubble contains universes with every possible set of physical laws. Universes where the speed of light is different, where gravity works differently, where there are more or fewer dimensions of space, where the electron has a different mass, where atoms cannot form, where chemistry is impossible, where consciousness as we know it cannot exist. All of those universes are real in this framework. All of them coexist with ours right now, separated from us not by distance in our three spatial dimensions, but by a boundary in the configuration space of physical law, by a transition in the vacuum state, by the topology of the larger reality that contains all of them. Something is out there right now, not in the past, not as an echo, right now, coexisting with our universe, governed by physics we cannot imagine, containing structures we have no concepts for, running experiments in the space of possible physical laws that we are a single data point of, and it knows nothing of us, has no concept of us, cannot communicate with us, is as indifferent to our existence as the ocean is indifferent to the individual bubble that forms on its surface and pops. We are a bubble in an ocean of universes. That has been here longer than our time has existed. That will be here after our last star goes dark and our last black hole evaporates and the quantum bounce or the conformal transition or whatever the physics says happens at the end of our cycle, produces another beginning in another bubble somewhere in the eternal churning of the metaverse. Now, I promised you unsettling, and I've delivered unsettling, but I want to end somewhere that is not just unsettling, because I think the unsettling part is only half the truth, and the other half is something that I find genuinely and deeply moving. Consider what it means that we can know any of this. We are beings who evolved on the surface of a small rocky planet. Our ancestors 4 million years ago were making stone tools and huddling against predators. 100,000 years ago, we were painting cave walls. 10,000 years ago, we were learning to grow food. 300 years ago, we did not know that galaxies existed. 100 years ago, we did not know the universe was expanding. 50 years ago, we did not know about Hawking radiation or the inflationary universe or the landscape of string theory or the Boltzmann brain paradox. And today, right now, in this moment, we are discussing with mathematical precision the thermodynamic properties of quantum vacuum states. In pre-Big Bang cosmological models, we are analyzing the polarization patterns of photons that have been traveling since the universe was 3800000 years old, looking for the signatures of what existed before we are building gravitational wave detectors sensitive enough to hear the echoes of density fluctuations in the first fraction of a second of cosmic time. We are writing down equations that describe the quantum geometry of space-time in the Planck epoch, before which classical concepts of space and time cease to apply. We are a bubble of knowing in an ocean of the unknown, and the bubble is growing. Not fast enough, not easily enough, not without the wrong turns and the false starts and the decades of confusion that characterize all genuine scientific progress. But it is growing. The boundary between what we understand and what we do not is being pushed outward, slowly, painstakingly, by the accumulated work of thousands of human beings who dedicated their lives to understanding things that are under no obligation to be understandable. The universe was here before us. Something was here before the universe. And we are the part of that long cosmic history that became complex enough to ask about its own origins. To look backward through 13.8 billion years of expansion and cooling and structure formation and read in the oldest light what the universe was like before we could have existed to observe it. To look further back than the oldest light using gravitational waves that pass through the opacity of the early universe without distortion. To construct mathematical frameworks that describe what came before the Big Bang in regimes where our normal concepts of space and time break down. We are the universe developing the capacity to understand itself. That is what we are. Not the purpose of the universe, but the universe has no purpose in the sense of an intention. But we are the part of it that is becoming conscious of the whole, the part that is building the map, the part that is learning to read the message that was written in the structure of space before we existed to read it. Something was here before us. And it made us not deliberately, not with any concern for the outcome, but through the blind application of physical law across scales of time and space that dwarf our imagination. The quantum fluctuations of pre-Big Bang physics became the density fluctuations of the early universe, became the seeds of the first stars, became the carbon and oxygen and nitrogen scattered across space, became the molecules of the primordial oceans, became the first self-replicating chemistry, became billions of years of evolution, became the neurons in your brain that are right now processing these ideas and feeling whatever it is you are feeling as you confront the scale and the strangeness and the deep improbability of your own existence. You are what the pre-Big Bang universe eventually produced. You are what was here before us eventually became, and the fact that it became something capable of asking what it was, capable of reading the fossils it left in the oldest light, capable of constructing the mathematics that reaches back before the beginning. That is the most remarkable thing in the universe. Not the universe's size, not its age, not the number of galaxies or the energy of the Big Bang or the precision of the physical constants. The most remarkable thing in the universe is that the universe produced something that noticed it was there. You are that something. Meditate on that.